Hey y'all, today we're going to be talking about combining functions and also composing functions and what each of those mean. So first we're going to talk about how to combine functions, and when I talk about function combinations, I'm really just talking about working with operations of functions. So like adding functions, subtracting functions, multiplying, dividing. So before we get started, let's go over some notation for these combinations, just so that you're familiar with what these might look like in certain problems. So first, let's say you wanted to add two functions together. So let's say we had f of x and g of x, and we just want to add them together. You can definitely see them written like this, but you might also see them written like this, f plus g of x. And these two things mean the same thing. I will more often than not use this form of this notation, but I want you to know that these two things are equivalent. If I were to subtract two functions like f of x minus g of x, I can write that as f minus g of x. So this notation is going to be pretty consistent. With multiplication, f of x times g of x, you can write that as f times g of x. Nothing really out of the ordinary here. If you were to divide two functions, f of x divided by g of x, you could write that as f divided by g of x. So this notation is just is probably new to you, but this is what it means. So this is just really like a shorthand notation for this. So yeah, this is what I mean when I say a function combination. I'm just talking about either adding, subtracting, multiplying, or dividing two functions. There's a little caveat with this last one. G of x obviously can't be 0 because you can't divide by 0. We'll just assume that's true for right now. So let's look at some examples of like kinds of problems that you're going to see involving these combinations. So let's say you've got two functions, one of which is f of x and it equals x squared plus 5. And another one that's g of x, which equals negative x plus 1. And I want to find, let's start with g minus f of 2. So I think the easiest way to approach this is going to be to evaluate each function when x is 2 independently and then subtract whatever those function values are. So if you understand this notation, you understand that what this really means is g of 2 minus f of 2. In other words, the value of the function g when x is 2 minus the value of function f when x is 2. So g is negative x plus 1 when x is 2. That gives us negative 2 plus 1. For function f, that's defined as x squared plus 5. So that would be 2 squared plus 5. From here, you just evaluate these. This would be negative 1 minus 2 squared is 4 plus 5 is 9. And negative 1 minus 9 is negative 10. So you will say that g minus f of 2 equals negative 10. Oops, let me scooch this up here for you. Let's look at another one. So let's say we had g times g of 4. So again, let's think about the definition here. This just means g of 4 times g of 4. So what we will do is evaluate the function g when x is 4. And really, since this is the same thing, we only have to do it once, and then we'll just multiply it by itself. So g is negative x plus 1. So that means this will be negative 4 plus 1. And so will this. So you get negative 3. Oops. Said 3, wrote 2. Don't know what's up with that. Negative 3 times negative 3. Which clearly is 9, so g times g of 4 is 9. Now these four operations you should be pretty familiar with. Addition, subtraction, multiplication, division. You've been dealing with these forever. But there's another way that we can sort of put functions together, and that is called a composition. So we can compose two functions, and that notation looks like this. We call it a composition of functions. So the notation goes something like this. F, and then you'll have a little circle, G. So this open circle is means composed with. So F composed with G. You might just read this as fog, but this is actually not an O. It's just an open circle, sort of aligned in the center of what you're writing, the top and the bottom lines. So F composed with G of X. Now what does this actually mean? This new operation? This just means that you are going to substitute G of X into F. So what that might look like, something that without using this notation might look something like this. F of G of X. And so those are two ways that you can read this, one of which you could say F composed with G of X, or you can just read it more like this, F of G of X. And what this means is you're going to substitute whatever the G function is into F. So you're just plugging this into this function. Whatever function is written to the right is what's being plugged into whatever's on the left. So X is getting plugged into G, G is getting plugged into F. Let me show you a few examples of how this plays out. So say we're given two functions. F, let's define as the square root of X plus 3, and G is X squared. So if I want to find the function F of G of X, then what I'm going to do is substitute the G function into the F function. This is the same thing as saying F of G of X. So in other words, we're going to plug in whatever G is into F. So G of X is equal to X squared. That X squared is what we're going to substitute into F. So basically what you'll do is rewrite the expression that F equals square root of X plus 3, but instead of writing X, you're going to replace every instance of X in F with X squared, because that's what G is. So that would be the square root of, instead of X, we're going to write X squared plus 3. Another way to sort of think about this is you're just going to plug in G into here. So I'll write this out to the side, although I typically won't show it like this. Square root of G plus 3. What's G? Well, G is X squared. So it's just another way to kind of think about that. You want to simplify as much as possible. So the square root of X squared is just going to be X. So we get X plus 3. Let's try another one. Let's switch it up. G of F of X. Now, before we actually work this out, let me just take a moment and think about whether or not you expect these two to be the same. Like if I plug in G into F, am I going to get the same thing as if I were to plug in F into G? Now, in general, they are not the same. There is a case where they would be the same, and we'll talk about that in a second. But in general, you would not expect that F of G is the same with G of F, unless there's something about the relationship between those two functions that we'll talk about momentarily. So G of F of X is just G of F of X, right? You're substituting F into G. So what is F? Well, F is root x plus 3. So we're going to take that entire expression and substitute it into the g function, which is x squared. So we're going to square this whole thing instead of just x. That is pretty much it. We still need to square this out to simplify it, but more or less this is going to be your answer. So when I square this out, I'd get x plus 6 root x plus 9. And if you're a little confused on how I made this jump, basically what I'm doing, and you don't typically have to write this if you understand how to get from here to here, is we're multiplying root x plus 3 by itself and just foiling this out. So first, outside, inside, oops, that should be a 3. Last, and then that's how you get here. Now going back to what I was talking about earlier, there is a case where these two things are the same. When these two things equal each other and they just equal x, then that means that g and f are inverse functions. So if f composed with g, or f of g of x, is equal to g of f of x, and that is equal to just x, then we can say that f and g are inverses. So there's quite a few inverses that you are probably aware of already. In this unit, we've talked a lot about logarithmic and exponential functions. So let me use those as an example to showcase when this is going to be, when this is actually going to happen. So if we let f of x be natural log of x, and we let g of x be e to the x, let's compare these two compositions. F of, oh wow. F of g of x would be what we get when we substitute g of x into f. So we're going to plug in e to the x into the x right here. So we get the natural log of e to the x. Using the properties that we've already talked about at the very beginning of this unit, we know as long as the base of this logarithm is the same as this base, so Euler's number, this is just going to equal x. Similarly, g of f of x would be what we get when we substitute f of x, natural log x, into g, e to the x. So we'll have e to the natural log x, which also just equals x. So both of these equal each other and they equal x, and therefore we can say that f and g are inverse functions of each other. Now we also want to be able to interpret these combinations and compositions graphically. So let's say I define two sort of weird functions for f and g, not as equations, but as just a graph. So let's label this like 1, 2, 3. We'll keep these numbers real simple so we can focus on the concept rather than getting lost in all the values. So let's say we define f as this piecewise function. So a linear piece from 0, 1 to 1, 3, and another piece from 1, 3 to 2, 0, and another piece from 2, 0 to 3, 2. So we're going to find this function as f of x. Then we'll create another function on here. Let's say it starts at 0, 2, goes down to 1, 0, goes back up to 2, 1. And then let's just say it ends off up in the same place at 3, 3, 2. So we'll call this pink graph g of x. From this graph, we can answer a lot of questions. And so let's just do a few. Like, I can ask you now, what is f plus g of 0? So this is going back to the combinations, just f plus g. The way you will evaluate this is by identifying the values of the functions, both functions at 0, and then adding the value of those functions. So f of 0 plus g of 0. F of 0 is 1. G of 0 is 2. So 1 plus 2 is 3. I want to reiterate that the value of the function is the y value. So when you're trying to find f of 0, what that means is you're using 0, this input, as your x. So the question is, like, what is the y value associated with x equals 0? So when x is 0, f is 1. Let's do another one. Let's say we have f times g of 1 equals, what was it? Kind of jumping the gun here. So f of 1 times g of 1. So f of 1 is 3. G of 1 is 0. So 3 times 0 is 0. We can also use this to find compositions. So let's say we want to do something like g, I have a bad habit of doing that, g of f of 1. So we're going to compose g of f and evaluate it for 1. Now you can do this a number of ways. One way to think about this is to actually find g of f. That's a lot easier, I think, if you have the equations. But if you don't, and you just want to sort of avoid the equations altogether, is to evaluate the inner function first and use whatever that output is as your input to the outer function. So if we write this in the other notation where we write it like this, g of f of 1, if we write it like this, I think it's a little bit more obvious what I'm trying to say here, which is we want to evaluate f of 1, find that value, the y value when x is 1 for f, and then take that number and plug it into g. So what is f of 1? F of 1 is 3. So what we're now trying to find is g of 3. So we want to find the y value of the point where x is 3 on the g function, and that's 2. Let's just do a couple more examples here just to kind of make sure that you guys get this. Let's do f of g of 2. So what this really means is we are going to find the value of g of 2 and then substitute that into f. So g of 2, we find g, x is 2, g is 1. F of 1 is 3. These kind of questions, I think, are a little bit easier because you're just evaluating. You're finding the x value and just sort of spitting out the y value and plugging that back in the other function. A more complicated question, or I think it's just the challenge is a little bit higher here, is when the unknown is not what the composition equals, but when I say, okay, well, this composition is going to equal a certain number, what x value would make that happen? So that kind of question will look like this. F of g of x, in other words, we need to find the x as opposed to finding y, equals 1. So another way to think about this is you want to say, all right, well, f of g of some number should equal 1. right? There's some output of 1 that an input, we're trying to find the input that will make that happen. So when the total output of the whole composition is given, you're going to work backwards. Instead of going from the inside out like we did on these, evaluate G of 2, plug that in, we're going to work from the outside in here. We're going to sort of undo the operations one at a time. So f of something is 1. So what does the something have to be? In other words, what does the input into f have to be to where the output is 1? Well, if we look back at the graph, where is, so f is going to equal 1 right here, right? So you think, what is the x value that would make f equal 1? Well, it would be 0, right? So if f of 0 equals 1, then that means g of x must be 0. If g of x is 0, we want to find what x value would have an output for g that's 0. So we look back at the graph and find, where's g equals 0? Well, g equals 0 right here. So the x value associated with that point is 1. G of 1 equals 0. So I might say, since g of 1 equals 0, x must be 1. All right, that's all for today, y'all. Start working on your homework. We'll be back next class on Friday. We'll review this unit. I'll take a few extra questions on the homework since I wasn't here to help you with it today, and we'll get ready for our Unit 7 test, which will be next week on the 22nd. So I'll see you on Friday.